So moving on and talking about intermolecular forces. So we talked about bonding, and bonding is intramolecular forces. So that's within a molecule. Intermolecular are between molecules. So, for instance, water. Water has a bent structure and is actually fairly attracted to itself. So the relative intermolecular forces are relatively strong as far as molecules for water. And it is very important for its properties. So these are attractive forces between molecules, and they're very important for many physiological processes. And water, of course, is very important for us as humans and other living creatures. Because of these intermolecular forces, it does certain things like carry nutrients throughout our bodies. Also, these intermolecular forces are the reason why matter exists as liquids and solids. So, what state the matter is, it depends on the types of forces. So, if there's a relatively strong force between the whatever is making up the material is going to be a solid. And liquid is kind of a medium force, and then a gas is a weak force. And remember, temperature is a measure of motion. At absolute zero means no motion, and then going up as things move around more, you can get to a point where there's enough energy that you can break the attraction between the different particles in the solid, liquid, or gas. So if it's solid, if there's enough energy, then the solid will melt, and if there's enough energy, then the liquid will boil. So it really depends. And so in a way, melting points and boiling points are a measure of how strong the forces are between molecules. And also, so solids are relatively sturdy. Liquids, they don't have a set shape, but they can move around. There's a little bit of freedom. And gases have the least amount of restrictions. So showing here solid, liquid, and gas. And definitions, we've covered this in previous chapters. So, and liquids, relatively high density, just like solids, but the gases have a less density. Liquids have moderate. Solids have the strongest, still condensed state. So similar to liquids, are condensed state, but they have the strongest intermolecular forces. And here's liquids and solids. So liquid is got the shape is whatever container it is put into. And solids such as ice, they're more fixed. They're not as free to move around as liquids are, but they do vibrate and rotate within whatever structure they're in. So they're still moving, but just not translationally. So let's talk about some other things. Surface tension. So surface tension is there is a certain network of energy at the surface, and if you've ever jumped into a body of water and belly flopped, you know how much that can hurt. Because if you hit it just right, the surface tension of water will give you a force right back, and it'll hurt. It can smack you. Then there's viscosity. Viscosity is the resistance to flow, so it prevents things from moving. So, for instance, here this fly fishing lure. I don't fish, so I don't know. I know there's bugs. We called them water striders that used to hang around the surface of water in the mainland where I grew up. But if there is enough surface tension, you can get things to float on the surface using that surface tension. So there's that side effect of the intermolecular forces of liquids like water. And this diagram here shows you where the surface tension would be then and the attractiveness between the molecules. Now, viscosity, resistance to flow, we have a saying, or at least I don't know if we still use it, but you're slower than molasses in January. So molasses, it's kind of syrupy. And of course, in cold temperatures, things move more slowly. So molasses in January, it's usually colder in January. So slow as molasses in January. That means it's very viscous and it flows more slowly. So certain things, motor oil, for instance, is more viscous than gasoline, and it depends on the type of molecule. The more intermolecular forces, so the heavier and longer hydrocarbons and motor oil, there's more attractive forces to them, and then the relatively shorter and branched uh, uh, hydrocarbons and gasoline. So because of that, motor oil has some resistance of flow. And I already mentioned maple syrup, but well, I said molasses. I think molasses is a little thicker than maple syrup, but it's it's still relatively viscous. So you can think about that as you're pouring some maple syrup over some delicious pancakes. Now I'm thinking about pancakes and less about chemistry. So let's move on and talk about evaporation. So when you have liquids, and we talked about vapor pressure before, there is a certain amount of vapor that's over the surface of the liquid, and we model that by saying that the liquid is exerting a pressure at the surface, and then the amount of the pressure of that liquid at the surface is the vapor pressure. But you can increase this by a few ways. Increase the surface area. So if you have a puddle instead of a glass of water, increase the temperature, that increases the vapor pressure, and also decrease the strength of the intermolecular forces. Well, that need to change substances or do something. So liquids that are easy to evaporate, we call them volatile, and things that are not so easily vaporized, non-volatile. And this process is evaporation, and it's actually it's an equilibrium process. But of course, if you have in this image here, you have the container open, the mass will just go away. So eventually, that will all evaporate away. But the liquid there is moving to its gaseous state. So it is a process that, in various temperatures, it can happen slowly. But of course, at higher temperatures, you can get the liquid to boil. So where does this come from? So if you look at this diagram here, on the x-axis, you have the kinetic energy, and the y-axis, you have the fraction of molecules. And the curve to the left in blue, you have lower temperature. Curve to the right, you have higher temperature. If you look at the area underneath the curves, it would be the same. So, and temperature means average kinetic energy. So it's the average. You can see both of them have molecules near the origin, meaning you have some molecules not moving at all, and then you have some that are moving really quickly. So that dashed line there, that is the minimum energy that's needed to escape the intermolecular forces of the liquid. And you can see at a low temperature, in the bottom, you have a small fraction of molecules that can escape. And a higher temperature, you have still a small fraction, but it's larger than the lower temperature. So that distribution of energy, where you have some that has enough energy to escape, that's the reason why we have a predictable vapor pressure of liquids at specific temperatures. And then the opposite is true for condensation. So evaporation is liquids go to vapor, and vapor then to liquid is known as condensation. And so they're opposites. And in a closed container, this would be a dynamic equilibrium, meaning that the rate of condensation is equal to the rate of evaporation, and then this process goes back and forth. And in a closed system, then the vapor pressure is then the partial pressure of the vapor over its liquid. And this illustrates here. So initially, you stopper it, and you have if you have a vacuum or atmosphere in there, some start to evaporate, and then it reaches a point where evaporation and condensation happens at the same rate, and then that is the equilibrium, and that is at the vapor pressure. How can you increase the vapor pressure? Increase the temperature, or decrease the strength of the intermolecular forces. So that's how you can do it. Boiling, when a liquid boils, anytime this is when the vapor pressure is equal to the ambient pressure, and when that happens, the process, the liquid starts to boil, and it's still a dynamic equilibrium actually. So this is still equilibrium, and also property about boiling liquids, they do not change their temperature. So if you are simmering water, so if you are cooking something and you have it simmering, the liquid on the inside is at 100 degrees Celsius at sea level. So depending on what your altitude is, but assuming a sea level, the inside temperature of the liquid is 100 degrees Celsius. if you turn up if you're cooking and you turn up the pot, you can get the edges of the pot to go higher than 100 degrees Celsius, but the bulk liquid itself will not get higher than 100 degrees Celsius. So you could even burn the food on the bottom of your container, but then if it's boiling, it's going to be at 100 degrees Celsius. So that's one thing about a liquid during a phase change, the temperature of a liquid does not change. That's true for solids too. Mostly, you can get a little bit of variance in a melting curve, but generally speaking, as solids melt, except for the beginning and the end, they are more or less the same temperature. So here's an example of a heating curve. So you look at the x-axis is the amount of heat. You can also think of it as time because you have something in the heater. And the y-axis is temperature. So you start off at a liquid, and you heat up, and think of a closed container. So like say you've got a water. You put some water in a vessel, and you screw the top on so it's sealed. And eventually the water is going to heat up, and it's going to start to boil. When it boils, it stays at 100 degrees Celsius, and then you get the steam, and then you can get to what's called superheated steam. So the temperature of the water vapor goes up, but I mean it's already boiled. So, but you can see that during the phase change, there is a constant temperature. So that's one way you can look at these, and you can. This is one of the ways we determine substances. Is we look at them and we heat things up. Not so much boiling, typically more with melting points, determine what's in the inside. And for evaporation is endothermic, meaning it absorbs energy. And this is part of the nature of evaporative cooling. So this is only part of the story. We don't talk about heat transfer that much in this class. When you're wet, the heat transfer coefficient changes for your skin, and wet things lose heat much more quickly than dry things do. So if you're swimming in the wintertime, you get out of the water, you notice that you get cold really fast because the wet surface is much more efficient at heat transfer. So it's two things. It's the evaporative nature of cooling. It's also the heat transfer coefficient. So that's part of our natural way of cooling, we humans, is the fact that we sweat. And this is a relatively rare thing for animals. So other animals don't have this ability. So humans are pretty good at expelling heat, but it comes at a cost because when we sweat, we get the water source is our blood plasma, so we can dehydrate quickly, much more quickly than our other animals too. So we're good at expelling heat, but we're also it makes us vulnerable because we're more likely to overheat. So, and with the water evaporation, also the heat transfer coefficient, that slows down. And with high humidity, it makes it harder for evaporation. So that's one thing that then you sweat. There's still a heat transfer, though, because of the heat transfer coefficient changes, but it's less efficient. So for condensation, evaporation is endothermic, condensation is opposite, it's exothermic. So if you've ever gone into a steam room in a gym, like for me, I get hot really fast. When I go in the steam room, that steam condenses and I turn into a lobster. I turn really, really pink because it releases that energy really quickly. So it releases that heat of vaporization, which we'll talk about soon. So this is where it goes back and forth. This is partially true of the bottom point, exothermic nature of condensation. So there's also the fact water vapor is the primary greenhouse gas for the Earth. So it corresponds to well over 80% of our greenhouse effect, lesser degree carbon dioxide. And much of that also happens in clouds. It also depends on where the clouds are. And when you're in the desert, you don't have as much heat carrying capacity in the air. So it's not necessarily with the water vapor itself and the cooling. It's also the fact of the greenhouse effect is lessened there, and so it's a combination of things. So it's not just that. So with coastal cities, it's not. It's also because of the ocean itself is a heat source. So when you're a coastal city, the coastal cities tend to have a much more consistent temperature throughout the day. It's cooler during the day and warmer at night. And I used to live in the San Francisco Bay Area, and just like Samuel Clemens said, and it's nothing's colder than a summer in San Francisco. So, or maybe he said the worst winter I had was a summer. I forget the quote, but it gets chilly during the daytime in San Fran. So the energetics come from the heat of vaporization. So and same idea with the heat of reaction. So this is a physical process. So the delta H reaction, this is said as delta H for a process. And the heat of vaporization for water is 40.7 kilojoules per mole. It's pretty high. So that's pretty high for water. And it means it takes a lot of energy to boil water. It also takes a lot of, and also when water condenses, it emits quite a bit of energy as well. So to show you this here, so vaporizing water takes 40.7 kilojoules, and then when water vapor condenses, it releases that latent heat as well. So it's quite a bit of energy. So here's a chart that shows the heat of vaporization at various points and temperatures. So you can see there, and water's is relatively high. So it's not, it's not going to be the highest, but it is relatively high, especially for how simple the molecule it is, just 3 atoms. So we can use this heat of vaporization to calculate the amount of energy it takes to vaporize that liquid. And why is this important? Well, for when we generate electricity, a lot of times we use steam to do that, and so we need to calculate that. Also, steam is used quite a bit in propulsion for Navy vessels, so they teach Navy personnel quite a bit on how to look at steam and how much energy it takes for steam to move around. So this is very important. Lots of applications in industry, civilian, and military. So let's do a problem like this. Calculate the amount of water in grams that can be vaporized using 155 kilojoules of heat. Well, vaporized at its boiling point, so we're not heating up the water. We're at its boiling point, so let's figure it out. So 155 kilojoules in mass of water. So from this we can figure out the number of moles of water we can get, and then from the molecular weight we can figure out the mass of the water. So let's go ahead and do this. So 155 kilojoules, and then the mole of water per 40.7 kilojoules of heat, and then 18 grams of water per mole of water, and we get 68.6 grams of water. Does this make sense? And looking at this seems about right. So it's going to be around 3 or 4 moles, and then at 18 grams, so that's going to be 60 to 80-ish amount. And so yeah, 72, that makes sense. So yeah, in my mind, I'm like, yeah, this kind of makes sense. And this is kind of like checking and thinking about your answer and seeing where it goes and seeing what ranges you're at. That's kind of how you can check these answers to see if they're right. So calculate the amount of heat in kilojoules to vaporize 2.58 kilograms of water at the boiling point. Okay, so we're we're doing the other way around. We're looking at the heat. We're looking at how much water we can go from the heat. Now we're looking at the how much water you can get from a certain amount of heat. Now we're going to see how much heat do we need for a certain amount of water. So same thing, but starting with 2.58 kilograms, 1,000 grams per kilogram, mole per 18.02 grams, 40.7 kilojoules per mole. So now we get 5,830 kilojoules. So that's quite a bit of energy. That's a lot of energy, actually. So 5,000, 6,000 kilojoules. That's like a day's worth of, maybe a small day. That's almost a day's worth of food. The amount of energy that's in a day's worth of food. So it depends on how much you eat. So that's a lot of energy. So we talked about vaporization. Let's talk about melting. And similar to the boiling point, the melting point is where atoms and molecules, they have enough energy to overcome the intermolecular forces to break the solid to turn them into a liquid. And so same idea that when ice is melting, for instance, and we're very familiar with ice and water and steam. So we're using these examples. And ice melts at 0 degrees Celsius. And as ice is melting, the solution is going to be at about 0 degrees Celsius. So once all the ice melts, then the temperature of the solution can rise. So here is a melting curve, for instance. And so if you take an ice cube out of the freezer and you put it in a frying pan and turn on the heat, and then measure the temperature at the surface of the ice, you'll notice that it starts out small, and then as it's heating up, you get to the point where the ice cube starts to melt. Now, as the ice cube is starting to melt, that entire solution is not going to go higher than 0 degrees Celsius, and because of the equilibrium process. The same thing with the boiling point at the equilibrium. You're still having that dynamic equilibrium, and then you get where everything is melted. Now it can go up in temperature. So this is partially true. You can get certain states. So one thing about solids, many of them are amorphous. If this was a perfect single crystal of ice, this would be absolutely true. If it was an amorphous solid, you would get the higher energy solid particles to melt first. So you might see a little melting that happens below 0 degrees Celsius. And for particularly stable parts, you might see a little bit of melting after 0 degrees Celsius, but you'll see it more at before 0 degrees Celsius. And you can also see another phenomenon called a supercooled liquid. So you can cool liquids down, you get to a point where it's kind of a semi-stable state, where you have the liquid that's below the melting point. And then if you give it a sudden shock, like you hit it or you put a crystal in there, then the whole thing can freeze at once. And it's really cool. It's really cool to do. It's fun to do. So whenever they tell me there's a hurricane coming, I'll put a bunch of bottles of water in the freezer, and after I set it for a while, I think it's a lot of fun to wait till it gets to the super cold state, and then I take out the water and I smack them, and then the whole thing just turns to slush in an instant. And I always like doing that, because that's the super cold liquid. That's always fun for me. So, but that's going the other way, and that's kind of a exciting thing. You can do that at home, and make sure you use a plastic bottle, not a glass one, because the glass can shatter in the freezer. So make sure if you're gonna do the experiment, make sure you get a plastic bottle so if you forget it, it won't shatter in the freezer. So let's talk about the energetics of melting and freezing. It's the same idea with the vapor phase, with the evaporation and condensation. So same idea, except you have melting for solid to liquid, and then you have freezing from liquid to solid. So it's really just the same idea. And although it tends not to be as dramatic, I mean, in terms of energetic-wise, the heat of freezing, the heat of fusion is not as high as the heat of vaporization. So let's see here. So we have the heat of fusion here. Heat of fusion for water is 6.02 kilojoules per mole versus 40.7 for the heat of vaporization. And depending on the direction, so fusion is endothermic. So it takes energy to melt ice, but then again, when water freezes, the heat of fusion is then emitted. So it depends on the direction where the energy flows. And the idea is that the heat of fusion, it takes energy to melt things because you're breaking the bonds, and then freezing is exothermic because the bonds are forming in the solid. So here it shows the direction. And we can use same idea as the vaporization. We can calculate it. And here are the various melting points and freezing points. And also you can notice a few things. Actually, freezing points or melting points, freezing points, and boiling points, these are a measure of how strong the intermolecular forces are. So water actually has a relatively strong intermolecular forces. Water is a weird substance. We'll talk about it more later. So let's do some calculations here. Calculate the amount of ice in grams that you can melt at 0 degrees Celsius that absorbs 237 kilojoules of heat. So, this is 155. This is the wrong one. So let's do this. And oh, good. Didn't use 155. So 237. Same idea with the vaporization, but we're using the heat of fusion instead. And then figures out from there. It figures out the moles of water and then the molecular weight of water, and then that means that 237 kilojoules can melt 709 grams of water. And does this make sense? And yeah, this in terms of all the amount. So 40 moles, about 40 moles is about 20 grams per mole, so it should be about 800 grams, and that's about 800 grams. So yeah, that's about right. So calculate the amount of heat when a 15.5 gram ice cube melts at 0 degrees Celsius. So we're having the heat. This is going to be endothermic, so the heat is going into the system. And let's figure this out then, as the energy is going the other way. So 15.5 grams of ice. So hopefully you think, oh, time to turn to moles. And then from that, then multiply the heat of fusion there. And we get 5.18 kilojoules. And then the direction of the energy flow, it's going into the system, so it's positive. So this makes sense. So sublimation, what is that? This is when a solid goes directly in the vapor state. So not everything has a liquid state at a certain temperature and pressure. You can have a solid state that goes directly into the vapor state. So dry ice, for instance, so carbon dioxide doesn't have a liquid state until about 5 atmospheres or so. So it doesn't have a liquid state at 1 atmosphere of pressure. So, but at a relatively low temperature, negative 78 degrees Celsius, there's enough energy for carbon dioxide to sublime. And that's the idea of dry ice. So it goes directly at this pressure of 1 atmosphere, it will go directly into the vapor phase, and that is called sublimation. And there's a few times, so ice in your freezer. So if you've noticed something, like sometimes you put like I do this sometimes. I feel healthy and I buy this big bag of peas and I stick it in my freezer, and it's sitting there. And then when I want to go eat them later, like 2 months later, I open up the bag of peas, and then there's like a snowball with peas in there. So like it's like a snowball with shriveled up peas. Well, what happened is that the peas, the water that's in them sublimed out of the peas and then condensed back down. Deposition. It goes from sublimation to deposition. So it deposits back down outside of it, and you get the sort of pea snowball if you have the bag of frozen peas. So, and I mentioned there. So yes, that's why you get pea snowballs. Maybe you have corn snowballs. I don't know. You can. So if you have this right now in your freezer, pause the video and go look at your various snowballs that you have in the freezer. And then going on to intermolecular forces. So the melting points and boiling points. This is a general trend that tells you how strong the intermolecular forces are. So the greater the intermolecular forces, the higher the melting and boiling points of whatever it is you're looking at. And for intermolecular forces, there's a couple different types. So the weakest force is known as the dispersion force, which is an induced dipole. There's a permanent dipole, a hydrogen bond, and then an ion dipole. So there's a dispersion force. This is also called the London force. Sometimes it's called the London dispersion force. But it all comes from temporary induced dipoles. So electrons are very fuzzy. They occupy a certain amount of area. And since the electron clouds are fuzzy, you can have, as two atoms approach each other, the electron cloud can cause the electrons in the other one to repel. And when that happens, then the electrons flow slightly away from the other electrons, and that induces a slight positive charge in the other atom, and then there is a very weak attraction between them, and that is called the dispersion force. And you can see it for noble gas like helium, and you have the ball of charge here, which is the electron, and the electron is kind of fuzzy. It's kind of occupies a certain amount of space, but as you have two atoms approach each other, it can polarize a little bit, so that's called the polarizability. And the strength of this ability to polarize, basically the bigger the atom and or molecule. Also, the flatter the molecule is, so if you're talking about a group of atoms, the flatter the molecule tends to polarize more, than the spherical ones tend to be more efficient. So for instance, imagine I have a piece of Velcro on the table, and I have a Frisbee with the other type of Velcro, and I have a basketball. So what's going to stick to the table more, the Frisbee or the basketball? And the answer is the Frisbee, because there's more surface area contact. So flatter molecules have a more surface area contact, hence more have a sense of polarizability. The more spherical shaped molecules are going to have less, so they have less dispersion forces. So that's the general idea for dispersion forces. Also size. The more massive the molecule, the more dispersion. The more electrons, the more dispersion it has. So this is a temporary dipole, and this is, I already mentioned, it's these from fluctuations, the electron clouds. And then because of that, there is an attraction between them. So then you have relatively weak attractions then between them from this polarization, and then if there's enough of this attraction, then you can have formed solids and liquids. And like I said, these are the weakest ones. And certain things like the noble gases, this is the only type of bonding between them at this temperature, at lower temperatures. So you can have some, at least you can ionize noble gases and they can have covalent bonding, but that usually happens in places like the sun. We don't really see that here on Earth as much. So it has to do with the polarization, and increases with molar mass, also changes with the shape. So if you look at the noble gases here, for instance, and the boiling point, it consistently goes up as it becomes more massive, but it's still pretty low. I mean, 165 Kelvin, that's still lower than negative 100 degrees Celsius, so that's pretty chilly. As far as helium, we're not even really sure if helium has a liquid state, or if it even has a solid state. This is something we can debate, because typically speaking, for solid and liquid helium, the distance between the nuclei and the atoms is about 5 angstroms, and that's like 3 or 4 times as far apart as liquid water is. So it's debatable if there is even such a thing as liquid helium, or if it's just a super cooled, just a kind of a solid, or not. If it's just a super compressed gas. It's hard to say. It's hard to say with this. So this is what we chemists do when we get into conferences. We spend lots of government money and we sit around and talk about whether or not helium has a solid or liquid state, and then of course we stay in fancy hotels, because why shouldn't we? Okay, so dipole force for all polar molecules. Let's move on. So we have London forces that are temporary induced dipoles. A little more powerful than that are molecules that have permanent dipoles. So these are not temporary, they are permanent, they sit there, and they are stronger, generally speaking, than the dispersion forces. And even polar ones have dispersion forces, but the polar molecules also have dipole-dipole forces, and they tend to be stronger. So since there's a permanent dipole and it's always sitting there, these molecules then have attractions for each other. These attractions, of course, are weaker than the attractions within the molecule. And to give you an idea, so dispersion forces go up in mass. So the dispersion force for formaldehyde is going to be about the same as it is for ethane, because it has about the same amount of mass. But you can see that the boiling point is considerably higher for formaldehyde than it is for ethane. And the same thing with the melting point. So I mean, it's the attraction within the formaldehyde is considerably higher. So there's much stronger forces. And again, higher boiling points, higher melting points mean that there is stronger attraction, stronger forces. So how does this work with miscibility? And we covered this a little bit before. Miscibility is the ability to mix. So generally speaking, polar liquids will mix with other polar liquids, and nonpolar will mix with other nonpolar. And generally speaking, polar tend not to mix with nonpolar, and vice versa. There's a few examples to this, though. Actually, ethyl alcohol, ethanol, will mix with both water and things like gasoline. They can do that, but water and gasoline don't mix. Water and ethanol mix, gasoline and ethanol mix, and water and gasoline don't mix. So there are a few exceptions to this, but generally speaking, like dissolves like. And you can see certain things like oil and water tend not to mix. And it's because of the types of attractions and the attractions they have for each other. So how do we determine if there's dipole-dipole forces? Well, remember, you cannot forget anything. You have to be able to draw the Lewis structure and do the VSEPR and look at the polar bonds and see if they add or subtract, and then determine if the entire molecule is polar. If the entire molecule is polar, then there are going to be dipole-dipole forces. If the entire molecule is not polar, is nonpolar, then there's going to be dispersion forces only. So to show you here, carbon dioxide, linear molecule, the dipole moments cancel. This one is going to be nonpolar, has only dispersion forces. Dichloroethane here is a polar molecule. It's tetrahedral structure, but it's not all the same bonding. So because of that, there is a net dipole moment, and then because of this, there will be a dipole-dipole force. So, methane, it's a tetrahedral, has all the same types of atoms. Because of this, it's nonpolar, so there will only be dispersion forces here. There will not be dipole-dipole. And a little bit higher energy, hydrogen bonds. So hydrogen bonds are a specific type of, it's a dipole-dipole, but it's when hydrogen is directly connected to a fluorine, oxygen, or nitrogen atom. Not just if they are in the molecule, but the hydrogen has to be directly connected to one of these. And it's sort of a really powerful dipole-dipole force. So it's just a little stronger than normal. We give it its own category, and it's surprisingly strong. The surprisingly strong attraction has certain things like the relatively high melting point of water. So you look at hydrogen fluoride, there's a pretty strong separation of charges here. And actually, hydrofluoric acid, in solution, they tend to form dimers, so the two molecules kind of hang out together. So it really is attracted to its neighbor. It doesn't necessarily form, in solution, at least water solution, it doesn't really form like clusters, but it tends to form dimers, like I said, and they really stick together. And so methanol, you have this OH group. That's also known as an alcohol. So you see the methanol, it's an alcohol. And the alcohol is that OH group attached to the carbon. So we call that an alcohol group. And it has certain things. And the alcohols, they have hydrogen bonds. And so because of this, you can see that the proton in the top methanol molecule that's attached to the oxygen, it has that pretty strong polar bond, and then it's attracted to the negative end of another methanol molecule. And so because of that, it's a relatively strong attraction and has a little bit stronger intermolecular forces. So if you look here, methanol versus ethane, I mean, methanol is slightly more massive, but if you look at the boiling point, it's much, much higher, even higher than formaldehyde. So you can see there is a huge difference in these. So it's a much stronger types of intermolecular forces going on here with methanol, and because of this huge difference, we give it its own category, the hydrogen bonds. And hydrogen bonding water is weird because it can give and receive two hydrogen bonds, and water has a pretty high melting point. So, especially for its molar mass, it's 18 grams per mole and has a boiling point of 100 degrees Celsius. This is really high. This is really high relative to other small molecules, and it's really kind of a unique thing. And water is really a unique substance when it comes to its chemistry. Let's move on and talk about ion dipole forces. So when you have a dipole liquid, for instance, or another molecule, typically in the liquid, you can have an ionic solid, and if there's enough the energetics are right, you can get the ion to dissolve in the liquid. And the liquid is usually water. And I've mentioned this before, and this usually is when it's low charges, like -1, and really big atoms and or ions. So chloride and sodium ions, these are big ions. So we have big ions with low charges, and because of that, the Coulombic attraction with them is not that significant. I mean, it's strong, but it's not as strong as, say, like something that's like +3 or +4 and a much smaller atom. So the alkalis are big atoms, a much smaller atom. It's going to be like if you have a lead +4 and an oxygen oxide -2. So that's an example of something that has a very big charge and a tinier atom or an ion. So those tend not to dissolve into water. But a small charge with a big atom, these can dissolve into water. And what happens though, so 6 water molecules surround both of them. And the idea is each of these have 6 attractions on the opposite charged ends. And the summation of all of these charges is greater than the attraction that forms it into its solid matrix that forms the crystal. So if this is true, then you can get things to dissolve. But the ion dipole forces, these are the strongest type of intermolecular force. And the reason for that is because here the sodium and the chloride, they both have full +1 or -1 charges respectively. So the water, for instance, has a partial charge, which means less than 1.6 times 10 to the -19 coulombs. So less than the charge of electron or proton. So whereas the ions have the full charge. And because of that, this is the strongest of the intermolecular forces. So let's take a look at the relative strength. The weakest are the London dispersion forces. Next are dipole-dipole. Relatively strong are hydrogen bonds. And hydrogen is only hydrogen is directly bonded to fluorine, oxygen, and nitrogen. It's not that there's just hydrogen with fluorine, oxygen, and nitrogen in the molecule. The hydrogen has to be directly attached to one of those. And then the ion dipole, this is very strong, and this is when you have things dissolve in liquids like water. So let's talk about how this works for an application. DNA has nucleotides, and we have the nitrogen bases, the adenine, thymine, cytosine, and guanine. And then we have, and this is how we encode quite a bit, most of our genetic material is found in the DNA molecules. And this is the general structure where you have the nitrogen base attached to a sugar. For DNA, it's deoxyribose. For RNA, it would be ribose. And then the phosphate group between them and the sugar to the sugar backbone. So this is the entire nucleic acid polymer. And also a certain key feature in DNA, it's a double helix. Adenine will always bond with thymine, and cytosine will always bind with guanine. Adenine cannot bind with itself, nor can it bind with cytosine or guanine. Same thing with thymine. Thymine cannot bond to itself, and so it can only bond with adenine. And it has to do with the hydrogen bonds, and specifically adenine and thymine, they bond in 2 spots, and it's oriented such that you can't bond the other one. And then the same is true for guanine and cytosine. They bind in 3 spots, and actually, so cytosine and guanine have a slightly stronger bond than adenine and thymine, but it's a relatively strong bond, but it's not that strong. So then you can have the helicase enzyme can come and unzip the DNA. And the DNA also has its own backup on the DNA strand. So the DNA can unzip, and then messenger RNA can also form on the DNA molecule. And then the messenger RNA can then go and form the proteins that actually do the function of the cells. And we've also learned about microRNA. MicroRNAs can activate certain genes on cells. That's the reason why you can have, like, all of us have the same DNA in our bodies, but we have muscle cells, bone cells, and nerve cells. And so the microDNA can activate cells. This kind of activate the genes. It's kind of cool how this all works out, right? The chemistry of life is pretty gnarly, you know. It's really interesting with that. But the fact that DNA likes to hang out together, but it's not so strong, you can't unzip it and get the information and zip it to replicate or make protein synthesis. So all this information is on there, and it's held together at least between the two strands by hydrogen bonds. So it's a relatively strong bond, but it's not so strong. It's not as strong as the intramolecular forces that hold the backbone together. So kind of cool, huh? So, okay, and we've talked about that, and this is for replication. We didn't talk about the protein synthesis and gene activation. That is bonus for you listening to this video. So let's talk about solids. We've talked about liquids, so let's talk about the different types of solids. There's molecular, ionic, and atomic, and crystalline can be broken down even further. So here are crystalline solids, and they can be molecular solids, and so it means the solids are made from molecules, and these tend to have relatively low melting points. And I know water, ice, and we said, oh, ice is so strong, it should be higher. But the thing is, compare the melting point of ice to the melting point of salt. It takes a lot of energy to melt salt, so ice is relatively low. And then atomic solids, we'll talk about atomic solids in a little bit. There's less, there's a little more variability in atomic solids. So we'll get to those in a little bit. So molecular solids, where everything is molecules. So ice, water, dry ice, solid carbon dioxide, these are molecular solids. And they're held together by various types of intermolecular forces. And these tend to be relatively weak compared to them. So these are going to have lower melting and boiling points with that. So, water ice melts at 0 degrees Celsius. It's held together by hydrogen bonds. Dry ice is held by dispersion forces. It sublimes at negative 78 Celsius. So these, generally speaking, are relatively low. And let's compare this to ionic solids. So these form formula units, and they're when you have the transfer electrons, and then they are held together into the solid lattice. Is kind of this matrix that holds all the cations and anions together. And these are relatively strong. So sodium chloride, it melts at 801 degrees Celsius. So compare this to carbon disulfide, a molecular solid with a higher molar mass. This melts at negative 110 Celsius. So you can see that the ionic compounds have a significantly higher melting point. So the intramolecular force, so the forces within the molecule, these are very strong and holding those ionic solids together. So it takes a lot of energy to melt them. So atomic solids, it depends. So it depends on the melting point. So we have like carbon, diamond, we have metal, iron, and then something like xenon solid. These are atomic solids, and it really depends. So diamond is an example of a covalent atomic solid, and these have a very high melting point. Non-bonding atomic solids like the noble gases, you can even argue that there is no solid state for helium. And then there's metallic atomic solids. So non-bonding atomic solids have very low melting points. And metallic ones, they have variable. So the atomic solids here, we have covalent like diamond and silicon. These have very high melting points. Then we have non-bonding like noble gases. These have very low melting points. And then metallic bonds, it's variable. It just depends. And so the covalent bonds, these are really strong. The intramolecular forces hold these things together very strongly, and then because of that, it's really hard to melt them. So like a diamond is estimated to melt at about 3,800 degrees Celsius. You got to ask yourself, what are you going to melt a diamond in? What are you going to melt that's going to be able to take something that hot? I mean, that's incredibly high. So then if you look at a diamond, it has this kind of hexagonal pattern, but everything is got a tetrahedral site. So a diamond is very hard. It is the hardest naturally occurring substance. Of course, boron nitride can be harder, but as far as natural occurring substances, diamonds are very tough. And they're very hard to melt. So something like xenon, it's only held by dispersion forces, so these have a very low melting point, so negative 112 degrees Celsius, that's not very high melting point at all. Let's talk about metallic atomic solids. We have to talk about what a metallic bond is. A metallic bond is kind of like a bunch of positively charged ions in this sea of electrons, and then the sea of electrons can flow around, and this explains a lot of properties about metals. Metals are ductile, meaning they're bendy. You can hammer them, and you can start hammering them and put them into different shapes, and they can still be molded and moved around. And so, but the fact that you have these positive centers and electrons flowing, it makes sense that this kind of physical property exists for metals. Also, metals conduct electricity extremely well, and heat too. So it looks kind of nice. So, but then you have things like mercury. Mercury melts at negative 39 degrees Celsius, and you have iron that melts at 1809 degrees Celsius. That's a pretty high melting point. So it's kind of weird with metals is that there's such a variation of the melting points with them. So this diagram here shows the sea of electrons, and really if you start hammering and moving the metals over, they still keep their metallic bond. So this electronic sea. Compare this to ionic compounds. If you start whacking an ionic compound, you can crack it really easily. So they're more brittle. Ionic solids are more brittle, whereas metals are much more bendy and ductile. And the bonding scheme here kind of shows that. And like here it shows a bunch of positive nuclei. I know the electrons are shown explicitly. I see them as this kind of fuzzy sort of gas that kind of flows around in it. So I see the artist's opinion of this, but in my mind it looks a little differently. So let's talk about water. I mentioned before it's really a remarkable molecule, and it's very important for the Earth, life on Earth. It has a pretty low molar mass, 18 grams per mole, but it's a liquid. So compare it to methane, for instance. Methane's got a mass of 16 grams per mole, so it's close to that of methane. But methane is a gas. And you keep on going. Maybe butane might start to get to the point where you're a liquid, but you really go up to octane, and that's over 100 grams per mole for a liquid. That's about the same as the range as water. So it's really a remarkable substance for its high boiling point and its long range of a liquid, and also the fact that it's a liquid at such low temperature and pressure too. So water almost wants us to be a liquid and wants to have the properties of liquids. And so the bent geometry gives it a really strong dipole moment, and then it allows water also to give and receive two hydrogen bonds, and which makes it a pretty strong melting point. And it's so polar, it's able to break apart. I mean, look how hard it was to melt salt, right? But water has the ability to rip salt apart without using high temperature. So it's able to just take 12 water molecules can break apart a sodium and chloride anion. So it's kind of crazy that it has that ability to do that. So because this water is great for transporting nutrients throughout the body, throughout the hydrosphere, of course it can transport toxins as well, but we can see it looks like there was liquid water, or it maybe was, or still at some point on the surface of Mars. So we'll see. We're still learning. Maybe we'll find out more. Maybe as of recording this video, no one's been on Mars yet. So we'll see if Elon Musk makes it there. And also the way water freezes is unique. It's what's weird is that the very common type of water ice is less dense. This is truly the exception to the rule. Solids always sink. And actually, there is solid water that sinks in water. So on the bottom of the ocean, there's different types of ices that are more dense than liquid water. So it doesn't mean that there is not solid forms of water that are that don't float. There are solid forms of water that do sink, and we do see them and in some places very thick layers in the bottom of the ocean. But generally speaking, and the more common type of water solid, there is it floats, and that's called alpha ice, or usually we just call it ice. So there are other types of ice, and this is not necessarily unique to water, right? Because carbon has graphite and diamond, so there's different structures of things. So water is not weird in that regards, but it's just weird that the more common one floats. And so also with the frozen layer there, it insulates the water, prevents further freezing. So imagine if if the common ice would sink, if that would sink, then it would just basically freeze out and kill a lot of things. So that's a nice feature for us here on Earth for life. And also, while water expands, and you might, if like I told you, when you put water in the freezer, get the super cold liquid, make sure you use plastic, because if you use glass, you can break the glass from that. So so because there's so many foods, and also us ourselves, you don't want to get frostbite. So those with high water content, they don't survive freezing very well, but you can flash freeze things, and then they don't necessarily align in that expanded phase, so that they don't rupture the cells. So, and that's a danger that you have with freezing, and with things like frostbite. You can get some really bad cellular damage. So here's the review. We talked about properties of liquids, property of solids, talked about evaporation and condensation, and also melting and freezing. Then we did a deep dive into intermolecular forces, talked about London dispersion forces, dipole-dipole, hydrogen bonding, ion dipole. And then, even I guess before that, we talked about things like surface tension and viscosity. We talked a bit about different types of solids and what the effects are, and we talked about the really uniqueness of water. So hopefully you enjoyed this section. Here are the learning objectives and legal. Thank you very much for listening.